Okay, so in this problem, a 15-kilogram ladder leans against a wall in the middle of an atrium of a large hotel. The ladder is 8 meters long. It makes an angle theta that is 60 degrees with the floor. The coefficient of the static friction between the floor and the ladder is mu static, which is equal to 0.45. How far along the ladder can a 60-kilogram person climb before the ladder starts to slip? Assume that the wall is frictionless. So I started out by drawing my pictures, and I drew them out and I spread them out. And instead of putting numerical values and confusing everything, I decided to put L for the length, and that's equal to 8 meters, and then for the length of the ladder, and then D is for the unknown distance from the bottom of the ladder and to the point where the person stands, and then M is equal to 60 kilograms, and then that was capital M, and then lowercase m is 15 kilograms. Now for the masses of the person and the ladder respectively, the weight of the ladder acts as the ladder's center of gravity. So again, that's the ladder's midpoint since it's in uniform. And now knowing all of that, I was able to apply the conditions for the equilibrium, starting with the sum of the forces in the x direction is equal to 0. I was able to find that the N sub W minus F is equal to 0, and then so then we know that F is equal to mu S times N times F, and then that's NW is equal to mu static, which is times N times F. So then after that, I decide to find my sum of forces for F of Y, which is equal to NF minus mg, capital MG minus mg, which is equal to 0. And then the only unknown quantity in this equation is m sub f. So I was able to solve for it. N sub f is equal to capital Mg plus mg, which is equal to capital M plus lowercase m times g. And then so now I can find NW because of this. So I set the equation. So noble force sub W is equal to U mu sub S times N sub F is equal to mu sub S times capital M plus lowercase m times G. And then I have all the expressions, and I just need to plug my values in really now, but I don't know the distance, which is the entire goal for this problem. So what I need to do is I set the net torque equal to 0. So the diagram shows that I chose the rotation axis at I found the most convenient choice is the axis is perpendicular to the plane. So and it passed through the bottom of the ladder. So 2 of the 5 forces are N sub F and F act at the bottom of the ladder. These 2 forces have 0 level arms, and therefore they produce 0 torque. So another reason why I chose this area right here is because the distance D is measured from the bottom of the ladder. So in this situation, the forces are either vertical or horizontal. So I thought it was easiest to use level arms to find the torques. So my 3 diagrams right here, I used the lever arm. I drew the line of action for each force, and then I drew the level arm, and it was perpendicular between the axis and the line of action. axis, but using the usual convention here that counterclockwise torques are positive, and that the torque due to the N sub W is negative, and the torques due to gravity are positive. I got the magnitude of each torque is the magnitude of the force times the lever arm, which was this equation. I think on the back right here. So it was the torque with the FR perpendicular. It is setting the torque equal to 0 yields this equation right here. Negative M sub W times L sine theta plus mg times 1/2 L cosine theta plus mg d cosine theta is equal to 0. So then I get that it's negative N sub W times L sine theta over mu g cosine theta plus 1/2 mg L cosine theta divided by mg cosine theta plus d equals 0. So I could find what the d is using this. So then I got d is equal to N sub W times L times the tangent of theta divided by mg minus m times L, and then that's 2 times m. So then we get d is equal to L times mg times m plus m times tangent theta divided by m minus m times divided by 2 m. So then I got 8, and I plugged in all my values for this. So then after that, I was able to get 6.8 meters, and h is equal to 6.8 meters times sine of 60 degrees, and then the height was 5.9 meters, and that is how I found this answer.